Rigid body in equilibrium. If a rigid body is in equilibrium, neither its linear motion nor its rotational motion changes. For two-dimensional motion, the x and y component of the net force are separately zero. In calculating the net force, we include only forces from external forces. So in addition, in linear motion, we must consider also the rotational motion, which also does not change the change under equilibrium condition. Okay? So this means that the net external torque acting on the object must be zero. So because torque is what causes rotational motion to change. So since we are dealing with equilibrium, object that is in equilibrium, so the x component forces, the y component forces, and the torque must all equal to zero. So we will use tau to represent torque. Okay, so let's have an example problem. Here, a woman whose weight is 530 Newton is poised at the right end of a diving board. With a length of 3.9 meters, the board has negligible weight and is bolted down at the left end, while being supported 1.4 meters away by a fulcrum. So this is the fulcrum, the triangle one. So find the force 1 and force 2 that the bolt and the fulcrum respectively exert on the board. So we have here the pre-bi diagram. So we have three forces acting on this system, and they are all only have y component. So we have F1, F2, and the weight of the diver or acrobat, sorry, or the woman, a diver, sorry, which is 530 Newton. So let's write 530 Newton. Okay, and we have here, we have set the direction of the torque, which is following the counterclockwise direction as our positive. And for the y component, x component is also here represented as our sign of the positive direction. Okay, so since they are in equilibrium, so the summation of x component is automatically zero because other than it is in equilibrium, we have no x component forces. Now let's solve for the y component forces. So we have, following the positive direction, we have F2 minus F1 minus the weight, which is equal to 0. And substituting the value of weight, so we're going to have F2 minus F1 is equal to 530 Newton. So we have now our first equation here. So since we have two unknown and we only have one equation, so we need another equation to solve for these two unknown quantities. Because when we're dealing or we are looking for two unknown quantities, we need two equations to solve this. And to get our second equation, we're going to use the net torque. The summation of torque, which must be equal to 0. Okay? So how we're going to get the value of torque? So first thing we have to do is to find or to set our axis of rotation. So from this figure, at what point we're going to set our axis of rotation. By the way, it's not necessarily to have a there is no specific or only one point of axis rotation in equilibrium. Since we are in equilibrium, at any point, take note of that, we have zero torque. So if I put here, or I will consider this one as our axis of rotation, so the summation of this is equal to 0. And if I put, or I consider this as our axis of rotation, this one at F1, so it's also equal to 0. If I consider this point at F2 as our axis of rotation, it's also equal to 0. So the location of the axis of rotation is regardless at any point of the system. So it is important that we have choose wisely we're going to put or consider our axis of rotation. Although it is not, even it is regardless at any location, but it is important to be wisely choose our axis of rotation because we have to eliminate some constant or we have to eliminate some value. Okay, so if I consider this point as our axis of rotation at where the woman standing, so I'm going to get still two unknown quantities because our weight will be equal to 0, but we have F2 and F1 that will be still unknown. But if I choose this at the point along the F1 as our axis of rotation, we can get F1 as 0, F2 is will the remaining unknown, and we have the value of W. Okay, so let's consider this axis of rotation along F1. And we have here the direction of the torque counterclockwise as our positive. Okay, so the torque for F2 now is equal to F2 times the length, which is L2 equal to 1.4 meter. And it is positive. And for weight, we have now minus weight times the length of the lever arm, which is 3.9 meter. And for F1, we have 0, okay, because we have no length or lever arm. And now it is equal to 0. Okay, so it's easy to remember the sign for getting the torque. So just look at the direction of the torque and the force. So since our direction of torque, positive direction is along, or since F2 is in direction along with the direction of the torque, they are both going upward. Therefore, the torque is positive. Unlike for the weight, which is opposite in direction, weight is going downward, and the length and the torque is the positive torque is counterclockwise going upward. Therefore, we are going to have a torque in the weight for the weight is negative. Okay, but consider this one. Sorry. If our axis of rotation is here at the middle, and we have here the forces F1, we have here F2, we have here F3, and we have here F4. And they are all have torques. Torque 1, torque 2, torque 3, and torque 4. And we consider the counterclockwise direction as our positive torque direction. Okay, so if you get the torque for F1, we're going to get negative torque because they are opposite in direction. For F2, we're going to have positive torque because they are both going downward. Same direction, positive. For T2, or for F3, force 3, we're going to get positive torque since they are both going upward at this direction. And for F4 or force 4, we're going to get negative torque since they are in opposite direction. So I hope you have understand that. Okay, I'm going to erase this one and continue solving for our problem. Okay, so back with our problem, we have now this net torque F2 times 1.4 minus weight 3.9 equals to 0. So substitute the value for weight, and we're going to get F2, if we equate this one, is equal to weight, which is 530 Newton times 3.9 meter divided by 1.4 meter. Therefore, our F2 now is equal to 1,476.43 Newton, since the meter will be cancelled. So we have here F2, finally, we have F2 is equal to this value, the magnitude. And for F1, using equation number 1, substituting the value of F2 at equation number 1, we're going to get F2 minus the weight, which is 530 Newton. So 1,476.43 minus 530 Newton. F1 now is equal to 946.43 Newton. So that's how we solve for a rigid body in equilibrium using this parameter, that the x component, y component, and the net torque is all equal to 0. Okay, so let's have another example. So in the figure, an 8-meter ladder of weight 355 Newton leans against a smooth vertical wall. The term smooth means that the wall can exert only a normal force, meaning that friction is equal to 0. And this force is directed perpendicular to the wall and cannot exert a frictional force parallel to it. A power factor whose weight is 875 Newton stands 6.3 meters up from the bottom of the ladder. Assume that the ladder's weight acts on the ladder center, and then like the hole's weight, find the force that the wall and the ground exert on the ladder. So we have now here our illustration and our pre-body diagram and our positive direction. And we are looking for the ladder's weight. We are looking for the force that the wall, this P1, we are looking for P1. And the ground exert, and Gy and Gx. So these are unknown values and we are looking for, so how we're going to solve for this one. Okay, so let's have our summation of fx is equal to gx minus p, since we only have two x component along x component forces, which is equal to 0. This is our first equation. So summation of fy is equal to gy minus the weight of the ladder minus the weight of the firefighter, which is equal to 0. So this is our second equation. Now for our third equation, we're going to get the summation of, sorry, we can solve now for gy, since we have the value the weight of the man, of the firefighter, and the weight of the ladder. So gy now is equal to 355 Newton plus 875 Newton, which is now equal to 1,230 Newton. Okay, so we have now our first value. So we have now gy. Okay, so next we're going to look for gx and p using the third equation, which is the summation of torque must be equal to 0. So we're going to consider the foot of the ladder as our axis of rotation. So we have now three forces that we have to consider. Okay, so summation of torque is equal to, for consider the P, we have P times. So what is the length or the height or the length of our lever arm for force P? So using the trigonometric identity of sine, so we have the length of the ladder, which is 8 meter times sine 50 degrees. Okay, and it is positive because they are along the same direction. Minus for the weight of the ladder, which is, the weight of the ladder is, we're going to substitute the value now directly, the value of the length of the weight of the ladder. The weight of the ladder is 355 Newton. So 355 Newton times the length of the lever arm, which is equal to 4 times cosine 50 degrees. And for the weight of the firefighter, which is equal to 875 Newton times the length of the lever arm, which is equal to 6.30 times cosine 50 degrees. And all in all, this is equal to 0. Okay. So now we can solve now for P by transposing this two term, and multiplying it by 8 sine 50. Okay, therefore, we're going to have 355 times 4 cosine 50 plus 875 times cosine, sorry, 875 times 6.30 cosine 50 all over 8 sine 50 degrees. Therefore, the value of P is equal to, where's my calculator? Okay, so the value of P is equal to 727.13 Newton. So this is the value of our P. And to solve for GX, using the first equation, and we know that Gx is equal to P, therefore Gx is equal to 727.13 Newton. Okay, so that's how we solve rigid body in equilibrium, considering the x and y component and the net torque. Okay, so now it's your turn to solve a problem. Check your understanding, solve this problem, and the figure for this problem is this one. Write your answer in the comment section. Don't forget to do that.